According to Albert Einstein, pure mathematics in its way is the poetry of logical idea. Today, we are going to learn an important topic from abstract algebra, a branch of pure mathematics, that is group theory. Hello everyone, myself Navya Joy, Assistant Professor, Department of Science, the Bhopal School of Social Sciences. So here we see our main objective. First, the history of group theory. Second, binary operations. Abstract algebra, and last, groupoid, semigroup and monoid. Talking about the history of group theory. In 1800s, people were knowing how to solve linear equations, quadratic equations, cubic equations and even quartic equations. But how to solve higher degree equations? Everest Galway came with an answer to this question. He used the tool group to solve higher degree equations. Later, group was a tool that is used to solve geometries. Soon it became clear that group is an efficient tool that is used in different fields of mathematics. Thus, group theory was born. Binary operations. Before moving into our main topic, let us recall some of the basic definitions. What is an ordered pair? Two real numbers x, y written in some specific order. We may see some examples. 1, 2, minus 1, 1. These all are the examples of ordered pair where 1, 2, minus 1, 1 are real numbers. Now, what is a Cartesian product? If we consider two sets A and B, the Cartesian product of A and B is A cross B, which is equal to the set of ordered pair xy, where x belongs to set A and y belongs to set B. Let us see an example. Let the set A contains elements 1 and 2, and let the set B contains the element 4 and 5. So what will be the Cartesian product of A and B? That will be equal to A cross B, which contains the ordered pairs 1, 4, 1, 5, 2, 4, 2, 5. This is the Cartesian product of the set A and B. Now, what is a binary operation? Let G be a non-empty set and the Cartesian product of G is equal to the ordered pairs xy, where xy belongs to set G. On applying the function or the operation star on the Cartesian product of G, if it gives an element of G, then the operation star is said to be binary operation on G. The image of any ordered pair AB which is belonging to the Cartesian product of G under the operation star is denoted by A star B. Now, we may see some examples. We consider the set of integers and the operation given to us is multiplication. So, what are we supposed to check? Multiplication from I cross I gives I or not. We should check this, okay? We will check this with the help of some examples. So here, since the operation is multiplication, so A star B will be equal to A into B, right? Now, let us consider any two integers. Let A equal to minus 1 and B equal to 2. So, A into B will be equal to minus 1 into 2, which is equal to minus 2, which is again an integer. So, this condition is satisfied. Therefore, we can say multiplication is a binary operation in G, that is the set of integers. Now, second example, we consider the set of natural numbers and the operation given to us is subtraction. So, what are we supposed to check? Function from the Cartesian product of natural numbers to natural number. Does this satisfy? So, let us consider any two natural numbers. Let A equal to 1 and B equal to 2. So since the operation is subtraction, A star B will be equal to A minus B. So A minus B will be equal to 1 minus 2, since we have considered the value of A is equal to 1 and B equal to 2. So 1 minus 2 will be equal to minus 1, but minus 1 is not a natural number. So this implies, this condition fail. This implies that subtraction is not a binary operation on G. Now we see the properties of binary operations. The first property is closure property. A binary operation star is closed on a set G if for every A comma B belongs to G, A star B is also an element of G. Now we may see examples. We consider the set of natural numbers and the operation given to us is addition. So here A star B will be equal to A plus B. So what are we supposed to find here? We are supposed to see here whether this A plus B, the element which we get after this addition, is a natural number or not. Let us consider two random natural numbers. Let A equal to 1 and B equal to 2. So A plus B is equal to 1 plus 2, which is equal to 3, which is again a natural number, which implies this condition is satisfied. So we can write closure property is satisfied. Now we consider another example. The set of rational numbers and the operation given to us is multiplication. Here A star B, that will be equal to A into B. Let us consider two rational numbers. Let A equal to 1 by 2 and B equal to 2. So A into B is equal to 1 by 2 into 2, which is equal to 1, which is again a rational number. So this condition is satisfied. So we can say closure property is satisfied. The next property is associativity. A binary operation star over a set G is said to be associative if for every A, B, C belongs to G, A star B star C is equal to A star B star C. Now we may see examples. We consider the set of natural numbers and the operation given to us is addition. So this condition will change into A plus B plus C is equal to A plus B plus C. So what we have to check? We have to check that whether this holds or not. Let us consider three natural numbers. Let A equal to 1, B equal to 2 and C equal to 3. Now first we will see LHS. 1 plus 2 plus 3. What is it? It is equal to 6. RHS. 1 plus 2 plus 3. It is equal to 6, which implies left hand side is equal to right hand side. Implies that this condition holds. So we can say that associativity is satisfied in this case. Now we consider the example of rational numbers with respect to multiplication. So the condition will change into A into B into C. Equal to A into B into C. We have to see whether this condition holds or not. Let us consider three random rational numbers. A equal to 1 by 2, B equal to 2, C equal to 3. So LHS will be equal to 3. RHS, that is 1 by 2 into 2 into 3. This is also equal to 3. Implies this condition holds. We can say that associativity property is satisfied here. Now we see one of the important properties of binary operation, that is existence of identity. Let star be a binary operation on a set G An element E belongs to G is said to be an identity element for the binary operation star if A star E equal to E star A equal to A for all A belongs to G. Now we may see examples. We consider the set of natural numbers. The operation given to us is multiplication. So here the condition will change into A into E equal to E into A equal to A. So for more easy method, let us give the value of A equal to 2. So I can write this as 2 into E equal to E into 2 equal to 2. So is there any natural number which satisfies this condition? Yes. E equal to 1 satisfies this condition. We already know that in case of multiplication, multiplicative identity is always equal to 1. We have already studied it in our school. So whenever this multiplication comes, 1 is the multiplicative identity. Now we consider the set of integers and the operation given to us is addition. So the condition will change into A plus E equal to E plus A equal to A. We consider the set of integers. Let me give value of A equal to minus 2. So I can write this as minus 2 plus E equal to E plus minus 2 equal to minus 2. Is there any integer value which satisfies this condition? Yes. E equal to 0 satisfies this condition, and we already know that additive identity is always 0. So whenever the operation is addition, we should always remember that 0 is the additive identity. So here we can say that identity element exists, and in the case of integers, the identity element with respect to addition is 0, and first example with respect to natural numbers, that is the operation was multiplication. Here the identity element is 1. The next property is existence of inverse. Let star be a binary operation on a set G and let E be the identity element of the set G for the operation star. An element B belongs to G is said to be inverse element of an element A belongs to G if A star B is equal to B star A equal to E, where E is the identity element. So we may see examples. We consider the set of integers and the operation given to us is addition. So this condition will change into A plus B equal to B plus A equal to E. So what is the identity element in case of addition? That is 0. So I can write this as A plus B equal to B plus A equal to 0. Now let me give a value to A. Let A equal to 2, which is an integer. So I can write it minus 2 plus B equal to B plus minus 2 equal to 0. So what will be the value of B? Minus 2 plus B equal to 0 implies B equal to 2. This implies 2 is the inverse of minus 2. Always remember that since this 2 is integer, we could say that 2 is the inverse of minus 2. If it was not an integer, we can't say that. It doesn't work in that particular case. Now, the next example is the set of rational numbers. The operation given to us is multiplication. So the condition will change into A into B equal to B into A equal to E. So what is the identity element in case of multiplication? It is 1. So I can write this as A into B equal to B into A equal to 1. Now let me give a value for A. Let A equal to 1 by 2. So I can write this as 1 by 2 into B equal to B into 1 by 2 equal to 1. So what is the value of B? 1 by 2 into B is equal to 1 implies B equal to 2, which is a rational number. So we can say that 1 by 2, 1 by 2 has an inverse element, that is 2, or 2 is the inverse element of 1 by 2. So, in both the cases inverse element exists. The last property is commutativity. A binary operation star over the set G is said to be commutative if for every A B belongs to set G, A star B is equal to B star A. We may say examples. We consider the set of natural numbers and the operation given to us is addition. So, what we are supposed to see is whether A plus B is equal to B plus A. So, we consider randomly two natural numbers. Let A equal to 1, B equal to 2. So, A plus B equal to 1 plus 2, which is equal to 3. B plus A equal to 2 plus 1, which is also equal to 3. So, we say that commutativity property satisfies here. Now, moving into our next topic, that is algebraic structure. A non-empty set G equipped with one or more binary operations are called algebraic structure. Let the symbol star, plus, dot, etc. denote binary operations on set G. So, what are the examples of algebraic structure? N plus, N minus, set of real numbers with respect to addition, multiplication, set of real numbers with respect to addition, subtraction. These all are the examples of algebraic structures. Now, moving into our last topic, that is groupoid, semigroup and monoid. The algebraic structure which satisfies only the closure property, that is called groupoid. The algebraic structure which satisfies first two properties, that is closure property and associativity, they are called semi-group. An algebraic structure which satisfies three properties, first three properties, that is closure property, associativity and existence of identity, they are called monoid. So, in this session, we have gone through the history of group theory, binary operations, properties of binary operations, algebraic structure, semigroup, groupoid and monoid. I hope this session was fruitful to you. Thank you.